Yeah, so the series is the sum of all the values of the sequences.
Getting closer.
Right.
Each individual term is getting closer.
Yep.
Not some of them.
Right.
Yeah.
What was our start?
If they had this conversion,
I thought that was I was thinking, so it's not sequence converges to zero. The series like it may not. But then
Luis and Matthew, talk.
yeah. Two series. But yeah, that makes sense because if these are positions of the one, but if it's very
I guess I was there's no this
Some of that is bad.
plus my parents were also open up doors to something.
Okay, for
It's not I have to
like all of the
use
values
that
and
for
programs.
and I take it with he's really good. It's just with his how good he teaches, he makes us test much harder.
The sum is a fighting.
That's why I took I said that he was a very good professor. He was always a good question. But the class was
Okay, is this what you said so far? The sequence is the list. It's just like you're listing these values and you just keep going. So the first one, the second one, it's just a list of values, like outputs of a function. Then you're making a big list of outputs of the function, okay? And then the series would be summing up all of those values. Summing up all those values. And so how do we write that? So we can write it explicitly or implicitly. So explicitly, what would that be?
Each value plus the next value.
Yeah, so it would be, tell me, A1 plus A2 plus, okay, and then we have some compact notation for that, which is sigma n equals 1, infinity, a sub n. What does it mean for the sequence to converge? That means as you continue out into the list, those values are honing in on a particular value until it's just indistinguishably close to that value. And then they get closer, and then they get closer, and then they get closer. So you pick any distance away that you want, and eventually the sequence will get within that distance and stay within that distance. But then pick a smaller distance, it'll eventually get within that, okay? All right, so if we're going to add all those terms together, under what circumstances will the series converge? Under what circumstances will the series converge? Tina, when will it converge?
Okay, so there's like multiple conditions. So if then the sequence AN converges to 0,
Okay.
then the geometric series will converge. But if it's harmonic series, it may not, or it will.
Okay, so you said if
The
sequence
AN converges to 0,
okay.
then the series may or may not converge.
Okay. So this harmonic series was just one example of when it won't. There are many other sequences that converge to 0 where the series, you add up the series and it does not. For instance, 1 over the square root of n, right? Which would be the p series with p equals a half. That gets to 0, the sequence, but the series is infinite. Okay, so this should make sense, right? How would it be possible for an infinite number of terms added together to be a finite value? How in the world could that be possible?
The sequence has to converge to 0.
Right, so eventually what you're adding has to get indistinguishable from 0. And then the thing has a fighting chance to actually sum up all those infinitely numbered terms to a value. So what if the sequence does not converge to 0, it converges to something else? Then what about the series?
Series is infinite.
Why?
Because you continuously add whatever value is not 0 to that series.
Right.
You just keep on adding forever.
Right, so if it converges to, 3 halves, your sequence converges to 3 halves, then just ultimately, what are you doing? If you're going to add all those terms together, you're just going to keep adding 3 halves plus 3 halves. That's just going to, if you think of the number line, you keep adding 3 halves, you're just going to get as big as you can. You're not going to add to a finite value. So the only way a series can converge, when does a series converge? If AN converges to 0, but only maybe. It's not a guarantee. Not only does it have to converge to 0, but it's got to converge to 0 fast enough. It's got to converge to 0. So there are some sequences that converge to 0, but the terms are still too big that when you add them all up, you get infinity. Okay? What if, so basically, if, let's see. So let's write out some statements here. Always true, sometimes true, or never true. If the sum of an equals L, then the sequence approaches 0 as n approaches infinity. Always true, sometimes true, or never true.
Sometimes true.
Always true, sometimes true, or never true. Think about it now. Got it? This is good. See if you understand. Always, sometimes, or never. How many people think always? How many people think sometimes? How many people think never? If the series converges, the series is converging, is it necessarily true that the sequence has to go to 0? Yes, this is always true. Always true. Okay, if the sequence goes to 0 as n goes to infinity, then the sum converges. Always, sometimes, or never?
Sometimes.
That's sometimes. You get it? You see how the first one is always? Always, sometimes, or never? Some people are saying always. Always, sometimes, or never. If an diverges, the sequence diverges, then the sum diverges. Always. Why? Because in order for this to converge, what has to be true? An has to go to 0. And then, so that's the condition that we need. So if an diverges, or if an converges to a non-zero value, that's another one. So that's always true. So write a fourth one. Everyone got this third one? Everyone got it? Okay, hurry. Can I do, yeah, ask me.
Like on the first one, suppose you have like an alternating sequence.
So?
So this still like converge the series.
Yeah, the alternating sequence, remember that the condition of the alternating sequence is that it's positive and decreasing. So let's see. Okay, so I guess all right, so how about if I did this? Is that better? Does that make it right now? Okay. Okay. Yeah, that's a good point. That's technicality there. Okay, and the last one. Always, sometimes, or never. I guess this is the same as the first one now again, right? If the sequence converges to L to a non-zero value, then the sum diverges. Always. Sometimes?
That's the sequence, or just the sequence, not the ratio.
Oh no, okay, this is not, okay, this was right, this was right. Because what's going to happen, Martin, if it converges, if it's alternating, then it's getting closer and closer, so it's like you're zooming in on, say, this. If it's not zero, say you're zooming in on this. So we get to the last. So we get way out in the sequence, okay? So you have this, right? That does not, the sum does not converge because it's going to go 0, 3, 0, 3, the sum. See? If you're adding these up, you add 3 and you're going to subtract 3. And you're going to add 3 and you're going to subtract 3. And you're going to add 3 and that's not conversion. The series. So it has to go to 0, even if it alternates. If the sequence goes to something non-zero and it's alternating, that's still, the sum will not converge. Because it'd be, when you keep adding terms, it'll hop back and forth. Do you see? Okay. So originally it was right. Okay. Okay, does this help? These are really important concepts. Okay, so now let's look at some Weber problems. So I'll just go through the list. And we can glance at them, and then you can say, oh, that was okay, or you say, no, do that one. All right, so let's just look at them here. So this was geometric. You had to figure it out first, figure out what the formula was, and then analyze it as a geometric. Okay, non-geometric, and basically you're looking at the sequence and using these principles that we just talked about. Right, so looking at this, if you just look at that sequence converges to what? 1, because you got k squared plus 14k over k squared plus da 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 da, right? So as k gets very large, the sequence, that goes to 1 as k goes to infinity. So what about the series? You're gonna, just as like in the end, so eventually, it's just like you're going to keep adding 1 plus 1 plus 1 plus 1 plus 1 plus 1. Divergent, right? Same, that's the principles we were talking about there. Okay? That is geometric. Is this less than 1? Cosine of 0.9 is less than 1. Convergent or divergent? This converges, right? Is a geometric with an R value less than 1. That's a converging geometric series. Make the formula. This is also geometric. This looks like your R is less than -1 here. R is less than -1, outside the range, divergent. Okay, so this is the idea of actually today's lesson. This is an easy version of what we call a power series. So we'll be talking more about these today if this one was. But these still completely attainable with what we talked about in terms of geometric series, but we'll get more in depth on these today. Okay, great question. So the sequence, convergent or divergent? To what? To what value?
0.
Just 0?
Infinity.
5/6, right? 5/6. As n gets really large, the 13 is negligible. And basically you're going to have, you're just going to basically have 5/6 for very large n. So the series, you're adding 5/6 over and over again. In the end, you just keep adding 5/6 infinitum, or whatever that word is. All right? And so 5/6 and yeah, positive infinity. Yeah. Okay. Okay, this you're going to split it up into the sum of two sums. The second sum is basically 1. So you're adding 1. In that second part of the sum, you keep adding 1 over and over and over again. Convergent or divergent? Divergent, right? You're adding 1, 1, 1, plus 1, plus 1, plus 1. This is what how you have to think and see these, okay? Looks like convergent power series, right? R is 4/7. So we're going to have to we'll pull a 7 out, pull a 1/7 out. That's our A value. And it says determine the sum. Yeah, so it's going to be A over, A will be 1/7 divided by 1 minus 4/7. Okay, so I'm just cruising through these. Please stop me if you want to ask a question or you need clarification. Don't hesitate to stop me if you need if you have a problem. Okay, again, split it up into 2. Add them together.
Can we go over this one?
This one right here?
Yeah, please.
Okay, so basically you have the sum of 2/10 the n plus 7/10 n, but it's from n equals 1, right? So we need, first of all, we need these to be n minus 1. So first of all, do you see that if I'm summing up a bunch of terms that are themselves a sum, I can just sum all these up first, and then sum all these up and then add those together. So this is the same as 2 separate geometric series added together. Would you buy that? If you're not convinced, all you have to do is write out like the first 4 terms of this, and then you'll see every other term added is this, and every other term added is this. So you could just gather all the odd numbered terms and gather all the even numbered terms, and then you'd have it this way. Everyone see that? Okay, so now this one, we got to get this to be n minus 1. That means we're going to pull a 2/10 out, right? Is it fair? Same thing on this one. 7/10 times 7/10 to the n minus 1. Now we do a over 1 minus r will be the sum of that, and then a over 1 minus r will be the sum of that, and then add them together. You good? Okay, so then there are these at the end. So number 11, number 12, is that one, number 13, number 14, had e in it and square root, and number 15. Requests of 11 through 15. The last one? Yeah, or the one that has square root? This one? Okay. So we'll do one of these. So we're going to do the limit ratio test for absolute convergence. So this right here is going to equal so I'm going to, when we do this, we're going to do lots more of these. So I'm going to go right off the bat. I'm going to do this. I'm going to change that to an plus 1 plus, or times, 1 over an. I'm going to do this form, so it just saves a step. Okay, so we're going to write an plus 1, the ratio, times the reciprocal of an, which is the same as dividing by an, and then it saves a step. Okay, so an plus 1 is e to the n plus 7 times square root of n plus 8 over n plus 6 factorial times n plus 5 factorial over e to the n plus 6 square root n plus 7. We're going to gather the like things together. So e to the n plus 7 over e to the n plus 6 equals e. So here's how you can think about this. It's really helpful. You have a certain number of e's multiplied together, right? How many do you have here compared to that? How many e's are you multiplying here compared to this one? One less, right? N plus 7 e's and then n plus 6 e's. So you got one less e in the denominator, so when you do that division, you get e. Okay? And then we're going to have, say, square root of n plus 8 over square root of n plus 7. What will that be as n gets very large? That will be 1, right? So as n gets really, really big, the plus 8 and the plus 7 will go away. Okay? And then we'll have times. So what do we have? N plus 5 factorial over n plus 6 factorial. What does that equal? 1 over n plus 6. Do you see it? Right? Because what n plus 6 factorial is n plus 6 times n plus 5 factorial. Because factorial means you multiply by factors that step down by 1 each time. So it'd be n plus 6 times n plus 5 times n plus 4. Well, that's just n plus 5 factorial. So all that you have left is 1 over n plus 6. Okay, so what does this equal? What is this limit? That goes to 1. That's just e. And that is 0. So the limit of the product is the product of the limits. So e times 1 times 0 is 0. Conclusion? Absolutely convergent, right? Because it's less than 1. That limit is less than 1. Okay, last one. Oops. So everyone had a different one. This is the one I got. So we could do this whole big thing for absolute convergence, or we could just look at the sequence. Look at the sequence. What does my sequence converge to? 1. So therefore the series? No, it's not inconclusive. What is the series? The sequence converges to 1. Divergent. You're adding. It's like you're adding 1. Eventually you're just adding 1 over and over again. Okay? So, I mean, so it's telling you to do the limit ratio test. For this problem, you don't have to. It's just, it's divergent. So the limit ratio test is kind of meaningless because it's going to diverge. But I guess we have to do it to see what the limit ratio test tells us in terms of the value that we get, and to get this one right. So we can know right off the bat that this is going to diverge, but we'd have to find what L is to answer this question, to see whether it says that, whether the ratio test says diverges, or it might say inconclusive, and we could say it diverges by something else. So it's either going to be B or E. It's going to be one of those two, depending on the value of L we get when we do the test, which it's going to be 1. Okay, so we're going to get n plus 1 squared, n plus 1 squared. That's going to be 1. So it's going to be this one, E. Conditionally, converges conditionally. That means it converges when it alternates. That's what we looked at the end of class yesterday. If it alternates, it converges, like the alternating harmonic is conditionally convergent. So an example of that is the alternating harmonic series. That converges when it alternates, as it is, but it does not converge if you take away the alternating effect. You get the plain old harmonic series, which we know doesn't converge. That's the idea of conditional convergence. It needs the alternating effect in order to converge.
So the ratio test is inconclusive when it's equal to 1?
When it's equal to 1. That's right.
So what test necessarily would we be able to decide that divergence under? Because isn't
This one or the one I have?
whatever that problem is?
The one I have? The other test, it's not really a test. It's just the idea that if a(n) does not go to 0, the series diverges.
Okay, yeah.
That's the theorem, or
Right.
test. Yeah. Yes, it's the test, the sequence test or something. Sequence test for divergence. If the sequence doesn't go to 0, series diverges. Yeah. Okay. So let's press on to new stuff. No quiz. Okay, so we want to talk about something called power series. Is that the name of 8.5? Is that right? Yeah, 8.5. Power series. So you had some real basic power series on your homework. And those were like this. So let's actually, first a note. The geometric series, and we talked about this yesterday, but I'm going to repeat it. N equals 1 to infinity, a sub n, r to the n minus 1, can also be written, do you remember? N equals 0. So we got to adjust this so we get the exact, that's not a sub n, sorry, it's just a, okay? So we have to adjust this so that we get the exact same terms, right? It's the sum's got to be equal. So when n equals 1, we get r to the 0. And when n equals 2, we get r to the 1. So we want the first one to be r to the 0, and then we want r to the 1, etc. So if n starts at 0, then we're going to do r to the n. And these will be exactly the same. You get the exact same terms. In both cases, the first term is a r to the 0. Do you see that? And in both cases, the second term is a r to the 1. Okay?
So they use that summation definition starting at 1 just because we started the first term?
We were thinking about sequences, right? We were thinking in terms of sequences. And we liked n being 1 first because it was the first term of the sequence, right? So it gave us a nice, it gives us that connection with sequences. But now that we're good at series, now we can see that we can start that index at 0, okay? We're talking about a sum. All right, so this is the way that, because power series are a type of geometric series, so this is the general form that they use instead, okay? So definition of power series. Is a series of the form. So it starts at 0, like we just talked about. Okay, so I want you to practice. I want you to write out the first 5 terms. What does that, all these letters and symbols, and exactly what does that mean? When you see this, what do you think? Write it out. When you see this, you think what? Write it out. Everyone should be able to do that. Okay, who's up? Yasmin, you want to do it?
So C is constant, since x to the n is 0 would be 1. Or it would be C.
So the first term is
C.
C naught. Okay, and then?
And then it would be CX,
Comma?
CX.
Comma?
Plus.
Oh,
This is a series word plus.
CX
1, the first C1, X, okay. Then,
plus C2X squared
there you go.
plus C3X cubed.
Okay, I think we got it now. That's good.
Dot, dot, dot.
So,
Yep.
forever, right? So how is it, there's 2 ways this is different than just this geometric series that we talked about. What's one of the ways this is different? There's 2 reasons it's different. Justin, what's one of the ways it's different than a geometric series?
I think the C carries the subscript.
And what does that mean? That it carries a subscript. So what does that mean? Before it was just A, right? And now it's carrying a subscript. What does that imply?
The constant changes.
Yeah, so you get different. The A is not constant for every term. You can have a different constant for every term. Changing coefficient. Whereas before, A was the same on every one, right? Okay, what else? Well, I mean, I guess it's just a choice of symbol. So what's the symbol? Instead of R, we're using X. So what we're leading towards here is that we're gonna have a function of X rather than thinking of R as a constant, and we're gonna We're going to sum this up. We're going to think of this thing now as a function of x. We could, you know, by changing x, we get a different value output. The output would be the infinite sum, and we're going to get a different output depending on the x that we pick. So x, like input of a function. Instead of a constant r value, okay? So what happens is we solve these just like we would have looked at in terms of convergence or divergence, just like geometric series, but now then there's a range of x values that will make it converge, right? So it's like we're looking at what are all values of r in a certain situation that will make it converge. So you get a range and what's called a radius of convergence, okay? So you get a range and a radius of convergence. So let's look at. Oh, I don't know. This one, for example. Okay, so what is this equal? I don't like this example. Okay, so although it doesn't, right, it doesn't fit the form because what's different? This is n equals 1 instead of n equals 0. Okay, so, but if we're just testing for convergence, if starting at n equals 0 converges, then certainly starting at n equals 1 would converge. We just wouldn't have the 0th term. So we just do the limit ratio test as we would. And we're going to have x to the n plus 1 over 2 times n plus 1 minus 1 times the reciprocal of this. Okay, and so then we got 2n minus 1 and then 2n plus 1 in the bottom. So that limit will be okay, so this will do what as n goes to infinity? Go to 1. And this will be the same as x, right? So what we're saying is, what? The absolute value of x has to be less than 1, right? In order for a convergence, this limit has to be less than 1. So, and that's as n goes to, well, as n goes to infinity, x is just x, right? X is just x. So we need this to be less than 1, which means that as long as x is between -1 and 1, this thing right here will converge, be convergent. So I'm trying to see this as geometric. Okay. Any questions on that? So there's what's called the interval. This is called the interval of convergence. Okay, this is the interval of convergence. Can I erase what I got up there? So we had this. This is called the interval of convergence. All values of x that make it converge. The rate, so then on a number line, let's draw that on a number line. So basically we're talking about this right here, right? So if you think of that thing like as a circle, okay? So imagine a circle that encompasses our interval. What's the radius of that circle? The radius of that circle is the radius of convergence. So what's the radius of that circle? 1. Or you can think of it as half of the width of the interval. The width of the interval is 2 from -1 to 1. The radius would be half of that, 0 to 1. Okay, let's try one with, let's try this one. Okay, so we want to find the interval of convergence and the radius of convergence. So we're asking, for what values of x will this thing converge? That's going to be our interval of convergence, and then the radius just comes out of that. Okay, so for what values of x does this thing converge? Well, we look at limit ratio test. And we're going to have n plus 1 squared, x to the n plus 1, over 2 to the n plus 1, times 2 to the n, over n squared, times x to the n. Okay, n plus 1 squared over n squared. 2 to the n over 2 to the n plus 1. And what else? X to the n plus 1 over x to the n. This limit is? Goes to 1. This is just the same as, this equals 1/2. And this equals what? X. And that limit goes to 1. So basically we have 1/2 x needs to be less than 1. So 1/2 x has to be less than 1 and greater than -1. Which means that x is less than, greater than. That's the interval. Radius is? Okay, questions on that? Please.
In that, when you went from the original problem to the second step, where did that -1 to the n go to?
Oh, yeah. I lost it. So it's going to be, we're going to have the -1 inside, right? So it should just be there should have been a -1 in there. So it'd be -1 n plus 1 over -1 to the n, which would be a -1. So does that change it? Let's see. Even when you switch it to less than, greater than -1, less than 1? Yeah. So it kind of flips it, but since it's 1 and -1, it's still the same. Yeah.
Because it's absolute value, so it essentially takes it out of it. You don't have to think about it.
Yeah. Okay, so the problems in the web work, so what I'm going to have you do is I'm going to give you one to work on here and see how you do. And then the problems in the web work are different than the ones in the book, and I wasn't expecting that. So I want to give you one to do, and then let me write it on the board. Look at some of the type in the web work. So let's just try see how this goes. Find the interval and radius of convergence for these two. Okay? Work together, or you try it by yourself first and then compare or get help from each other. And I'm going to look into this web work a little bit. First one's okay? All right, second one, should we try it? Okay, here we go. So we want to find the interval and radius convergence. We'll use the limit ratio test. So we'll have x to the 2n plus 1 over 2n plus 1 factorial. So you got to be real deliberate here. When you got the 2n in here, you got to be real deliberate. You're increasing n by 1, okay? And then times 2n plus 1 factorial. Negative 1 to the n. Nope. That's in the denominator. Over x to the 2n plus 1.
Is it a bad approach to just leave that negative 1 to the n out?
It's not bad, but if it were like negative 3 or negative something else to the negatives, then if you leave it out, you get it wrong. Okay. So, but in this case, yes. So you'll have a limit n goes to infinity of negative 1 times. All right. So what do we have? X to the 2n plus 3, which gives us in the denominator. What does it give us? So we're going to have 2n plus 3 and 2n in the denominator plus 1. So how many x's do we have in the numerator? X squared. Okay? In the denominator. So we have 2n plus 3 factorial and 2n plus 1 factorial. So you're going to have the 2n plus 3, and then the 2n plus 2, and then 2n plus 1 factorial, which will cancel out with the one on the top. So is this what you guys got? Okay, and so as n goes to infinity, what is this limit? Doesn't matter what x is. Doesn't matter what the value of x is. The limit is 0. So it converges for what values of x? All x. Doesn't matter what x value you pick. That limit's going to be 0. So this thing converges no matter what value of x you pick. Does it make sense? So what's the radius of convergence? Infinity. Well, that's the interval. Yep. So all real numbers is the interval. The radius is infinity. Okay, so on these problems, they have you actually type in the words plus infinity, and you actually have to put the underscore, okay? So it's going to say, if in this case, like this, they're going to say type in plus underscore infinity. And if you don't put the underscore in, it doesn't give you the credit, okay? It says it's wrong. So this is just for web work. This is just for web work. You'll see it. It'll say, give the radius convergence as a value or plus infinity, and you have to put plus underscore infinity to actually get the green bar, okay? Does that clear up the question on this one? Yasmin?
Yes, that's right. Can you tell us the answer to A?
Sure. Answer to A is going to be, looks like we're going to get, in the end, we're going to get x 3 x over 3?
Yeah.
Less than 1? So 3 is less than x is less than. So there's your interval, radius 3. Okay, so let's look at Okay, so there is something that comes up on these alternating ones here. So I'm seeing if it doesn't. So this on this particular one, we're okay because it goes to 0. But I want to do another example where the alternating makes a difference. Okay, so let's do another example where the alternating effect actually comes into this. Okay, so how about this one? Okay, so limit ratio test. We get -1. So the -1 to the n plus 1 and the -1 to the n is just going to give us -1, right? So we're going to have x to the n plus 1 over n plus 1, 2 to the n plus 1, times n, 2 to the n, x to the n. And we're going to have x over 2, and we're going to have n over n plus 1. And so this goes to 1, right? And so we have x over 2 less than 1. And we get -1. So I'm kind of flying through this because it's a little bit easier up to this point. Radius equals 2. Good so far? Now, so we have this alternating situation. We want to look, let's take a look at what happens when x equals -2 or 2, okay? So according to this interval, -2 will make this diverge and 2 will make this diverge because they're not in the interval. But let's go ahead and plug in x equals -2 and x equals +2 and see what we get. Okay, so if x equals -2, we get -1 to the n times what? 2 to the n times 2 to the n. And if x equals 2, we get -1 to the n times, oh sorry, I blew that. So this is -2. The whole point is this is -2 in here. Okay, sorry. And then this is +2. Okay, so what is -2 to the n over 2 to the n? -1 to the n. And what's -1 to the n times -1 to the n? It's just 1 to the n, which is 1, right? So this whole thing becomes, what does it become? This, and this all go away. And it becomes 1 over n. Convergent or divergent? Harmonic series, divergent, right? What about this one? What do we get here? Two to the n over 2 to the n is 1. So for this one, we get -1 to the n over n. Convergent or divergent? This is the alternating harmonic series. Remember that? Which converges. Therefore, we have to go back to our interval. And how do we change our interval? So remember, these are all x values for which it converges. So we need to adjust that. How do we adjust it? 0? We were testing x equals -2 and x equals 2. And what did we conclude? It converges at 2. So how do we have to adjust this interval? So now at x equals 2, it's okay. Yeah, so we're going to include 2 in the interval now. Does it change the radius? No. So 2 actually gives us the alternating harmonic series, which is convergent. So our radius is still 2. The interval is still from -2 to 2, but now we include +2, because when we include +2, we get that convergent series. Make sense? So the reason we didn't have to do it on this one is because it just went to 0, right? It just went to 0 and everything converged for all x. So that didn't make. But when in other cases like this one, when you have the alternating, you want to check the endpoints. So plug in your endpoints and see what simplified series you get, and see if one or both of those converge, and change your interval to include the endpoints where it makes it converge. Does it make sense? Anybody have a question?
Can we get into application of these?
What's that?
Do we get into application?
We do not. We do not. But there are applications. Ready to go on? Did I lose you? Are we good? Okay, so here we go. 8.6. Representing functions with power series. Okay, so let's think about this function right here. What does that kind of look like that we've seen? Something over something minus something. So this function has the form of the sum, the total sum of a power series. So what would A be? 1, and R would be x. So therefore, what does it equal? Let's use our n equals 1 form. Remember what it is? So how A and R forms the geometric series? A times R to the n minus 1, right? So 1 times x to the n minus 1. Okay, so let's write out the terms of that. First term would be n equals 1 gives us 1 plus, second term, x, third term. So we get this what? Infinite polynomial. Okay? Radius of convergence, right? So what's the radius? So here we don't have to do the limit rate if it's just the if we know it's a direct geometric series, then we know that x has to be what? Between 1 and negative 1, right? So what are we saying? We're saying this function right here can be written as a polynomial of an infinite number of terms for when x is between negative 1 and 1. Let's do it. This is cool. There are my kids. Where am I writing here? There it is. Okay. So what I'm going to do, I'm going to graph the function 1 divided by 1 minus x. That looks like that. Zoom in once. No, I don't like zooming in. I want that view right there. Okay, so there's 1 minus 1 over x, and we're going to compare that to y equals, first of all, 1. Good approximation? No, terrible, right? So let's change it. This is this blue. So plus x squared. Oh, see it's taking shape here. Plus x cubed. And what are we looking at? We're looking at between negative 1 and 1. So even 1 plus x squared plus x cubed is starting to take the form of the, so the red one is our infinite series, or polynomial version, and then the blue one is the 1 over 1 minus x. So let's add another one, plus x to the 4th. Plus x to the 5th. You see what's going on? The more terms that you add, the better this red one recreates this one. And so how could we recreate it exactly? How could we recreate the 1 over 1 minus x exactly? Between negative 1 and 1. You need all infinitely many terms. You need the infinite polynomial. You need to keep going, right? And the further that you go, the better you do. So now you can see it's black, right? Because it's like, oh, they're on top of each other. So this is the first 8 terms. Here's negative 1, and here's 1. So the more terms we add, the more this red one. And then if we zoom out, what about outside negative 1 to 1? Totally different, right? So it's just in that interval from negative 1 to 1 that this polynomial will, if you keep adding all the terms to infinity, you'll get the same graph, right? You'll get the same exact graph. Pretty cool. Okay, so let's try, and then what would 1 over 1 plus x be? Well, now a equals 1 and r equals negative x. So 1 over 1 plus x would be one times negative x to the n minus 1 which is negative 1 to the n minus 1 times x to the n minus 1 which if we do that shift, we just shift it to n equals 0. It would be negative 1 to the n, x to the n. So it would be the exact same one as before, but it would alternate. It would be 1 minus x plus x squared minus x cubed plus x to the 4th minus etc. And we could do the same thing. We could graph 1 over 1 plus x and then start graphing and adding terms in this polynomial. And the more terms we add, again, the radius of convergence is going to be between 1 and negative 1. And then here we'll have to check 1 and check negative 1 to see, like we did, because it's alternating. But this graph, the more terms you add, the better it will represent 1 over 1 plus x between negative 1 and 1. And if you add all infinite number of terms, you get the exact graph between negative 1 and 1. Okay, so let's do a harder example here.
I have a question.
Please.
So why does it go from n equals 1 to n equals 0? Does it matter?
Remember we had that for the geometric series. We had the, I showed you that it could be both ways. Just that equals that. It's just a little cleaner, right? So with this negative 1, it's just a little nicer to have them to the end. But that was that note at the beginning of class. I said note, you could start at 0 and shift the index. Okay, so let's try this one. See if you can do it. Bless you. Okay, did you get this? Okay, so we want to put it, if we were to put it in the form of our standard power series that we talked about, let's find the coefficients. So find C0, C1, C2, C3. So we want to get it to look like this form right here. Okay, so what does that mean? That means x to the n. Well, we got this 4 in here. So we got to get that 4 out of there. How does that 4 come out of there? As 4 to the n, right? And then it's x to the 2n. So this is going to give us our coefficients. This is like our Cn coefficients. And then we've got x to the 2n. So what we're going to do is we're going to write out the terms of this and the terms of this and see how we can figure out what terms Cn do we need so that it would have this form. Okay? So this thing right here equals, what does it equal? So when n equals 0, we get 5 x to the 0. Right? And then we get plus 5 times 4 times x squared. Right? Plus 5 times 16 times x to the 4th. So this is x equals 0, x equals 1, x equals 2, x equals 3 would be, or n, sorry, n equals 3, 5 times 4 to the, yes. What is it? 32? 64? X to the 6th. So notice we don't have the even powers. So if we were to write out this, let's compare it here. What does that equal? C sub 0 x to the 0 plus C1 x to the 1 plus C2 x squared plus C3 x cubed plus C4 . So to make it look like this form, we're asking what would the coefficients be? What would C0 equal? What would C1 equal? What would C2 equal in this, our standard power series form, to create this series? Write them out. So what would you need for these coefficients to make it work? Did you get it? Kevin, did you get it? So what would C0 have to be? No, but so what is C0? 5. There it is. That's our coefficient of x to the 0. What would C1 have to be? So that this equals this. What would C1 have to be? What's our coefficient of x to the first in this sum?
0.
0. There's no x to the first term. It's got to be 0. Do you see? There's no x to the first. So what do you have to multiply by to get this, right? Do you see? Yes? C2? 20. C3? 0. C4? Is that what that is? 320? Just 80, right? 5 times 16. Okay, C5. C6. Is that 320? You're just one ahead. In our sum, there's no x to the first term. So what would C1 would we need to make that right? We need C1 to be 0, so we don't have an x1 term. You see? If it's anything else than 0, then you're going to have something x to the first, which we don't have here. And C7 will be?
0.
Okay, so what's the moral of the story? This infinite polynomial right here, if we keep going, what? Gives the same function as that, for a certain radius, right? So we could solve this and find the radius of convergence, just like we did earlier. And for the values of x for which this converges, this infinite polynomial equals this function in that range. Okay.